generative AI is, well, it's everywhere these days, isn't it? Creating text, images, even music, seemingly out of nowhere.
Yeah, it's all about making something brand new based on patterns it's learned.
Exactly. And then, like in a totally different corner of the universe, you've got quantum computing.
Yeah.
Which is just mind-bending stuff, promises computational power that's hard to even wrap your head around.
Right.
So what actually happens when these massive fields don't just exist near each other, but really start to interact, collide?
Well, that collision, that's precisely what we're going to dig into today. Quantum Generative AI, QGAI for short.
And look, this isn't just pie-in-the-sky thinking. This deep dive, it's grounded in a whole stack of source materials you shared with us, research papers, articles right from the edge, your notes, all exploring this really fascinating meeting point.
Mm-hmm. Our goal here, our mission, if you like, is to unpack the basics, the foundations, to understand how QGAI is trying to harness the unique power of quantum mechanics specifically for these creative tasks.
And we'll look at the actual models being developed now.
Absolutely, the cutting-edge stuff. And really crucially, we need to look at what the current state of quantum hardware actually means for QGAI's future in the real world.
So think of this as your way in. You get a clear, informed view of QGAI, the big ideas, the surprising details, without getting totally swamped by the jargon.
Exactly. Let's set the stage first. We should probably start with the tech you're likely already familiar with, classical generative AI. And the key thing here is it's not just analyzing data, its whole point is to create new stuff.
Right. Not just spotting the cat in the picture, but painting a whole new cat that's never existed before. How does it actually do that, fundamentally?
Okay, so at its core, classical Gen AI learns the sort of hidden rules, the underlying probability distributions within huge data sets.
Probability distributions.
Yeah.
The chances of certain features appearing together.
Precisely. Imagine it sees millions of cat pictures. It doesn't just memorize them. It learns the statistical catness, the typical shapes, the colors, the textures, how they tend to combine. Then it uses those learned rules to generate brand new images that follow those rules. They look like cats, but they're not copies of any cat it saw.
So it's learning the deep structure, the likelihoods, to make new examples that fit.
You got it. And it uses really powerful algorithms, usually neural networks, trained on just massive amounts of data to figure out these patterns. And like we see every day, you can often guide this with simple text prompts.
And the sources we looked at, they highlighted some interesting design ideas behind it too, like generative variability, the ability to churn out lots of different but still appropriate results. That seems vital for brainstorming or giving users real creative options.
Definitely. And also this idea of co-creation. Designing the AI not just as a tool that does what you say, but more like a partner, a collaborator in the creative process itself.
And we're seeing this pop up all over. The sources mentioned finance for spotting complex fraud or creating personalized investment plans.
Pharmaceuticals too, designing potential drug molecules.
And retail. Personalized recommendations, sure, but also virtual try-ons, or generating those incredibly realistic product photos you see online.
It's clearly super powerful. But the sources are also clear. Classical Gen AI isn't perfect. It hits limitations, things like mode collapse.
Where it gets stuck making the same few things over and over.
Exactly. Limited variety. Then there's overfitting, where it learns the training data too well and can't generalize. And just the sheer computational cost. Training these huge models takes enormous resources, enormous energy.
Yeah, the compute demands are pretty staggering.
And of course, there are big ethical questions too, deepfakes, misinformation, but that's maybe a whole separate deep dive on AI ethics.
Right, a huge topic on its own. But just focusing on the technical limits and those compute costs, that really sets the stage for why people are looking at quantum. But before we jump there, maybe we should quickly touch on how some of the main classical models work, just the basics.
Good idea. Helps to understand what QGAI is building on or trying to improve. So the sources mention a few key ones. First, GANs generative adversarial networks, that famous 2014 paper. The core idea is this adversarial, this game-like setup.
The generator versus the discriminator.
Exactly. One network, the generator, tries to make fake data, say, fake images that look totally real. The other network, the discriminator, tries to tell the difference. Is this image real? Or is it fake?
So they're constantly trying to outsmart each other. Like an art forger getting better because the detective keeps improving.
Perfect analogy. They push each other to get better. GANs are famous for making really sharp, really realistic samples, especially images. But that training process, that adversarial battle, it can be really unstable, hard to get right, and it's prone to that mode collapse problem we mentioned.
Okay, so powerful but tricky.
Right.
What about VAEs, variational autoencoders?
Right. VAEs came out around 2013. They take a different approach, more probabilistic. Instead of the adversarial game, they learn a sort of compressed representation of the data called a continuous latent space.
Latent space.
Oh.
Like a hidden map of the data's features.
Kind of, yeah. An encoder network squishes the input data down into this probabilistic map, this latent space. Then a decoder network takes points from that map and reconstructs the data, or generates new data by sampling from that map.
And they're easier to train.
Generally, yes. They used a clever math trick, the reparameterization trick, that made training more stable using standard methods. They give you this nice probabilistic view. Historically, though, the samples they generated could sometimes look a bit blurrier than the best GANs.
Okay. And the current superstar, especially for images, seems to be diffusion models.
Yeah, diffusion models have really taken off. The basic idea has roots going back to 2015, but they really hit their stride around 2020. It's a fascinating concept. You learn to reverse a process of gradually adding noise to data.
So you start with a clean image, deliberately mess it up step by step until it's just random static.
Right. And then you train a model to undo that process, to take the static and step by step clean it up, remove the noise until you get back to a clean image.
That sounds complex.
The results are amazing, though. They generate incredibly high-quality, diverse images, and the training is much more stable than GANs usually are. The main drawback, historically at least, was that generating a new sample took time because you have to run through all those denoising steps. But they're getting faster.
And finally, transformers. We hear about them constantly with language models like GPT.
Mm-hmm. Transformers weren't initially designed just for generation, but their architecture, especially that self-attention mechanism from the famous "attention is all you need" paper. Well, it revolutionized how we handle sequences like text.
Self-attention lets away the importance of different words, no matter how far apart they are in a sentence.
Exactly. And crucially, it allowed for much more parallel processing during training. Now, the decoder parts of transformer models, like in the GPT series, are used generatively. They predict the next word or token in a sequence. They're incredibly versatile, scale amazingly well, but yeah, they need massive, massive amounts of compute power, especially for long texts.
Okay, so you see this pattern. Amazing progress, but hitting walls, training difficulties, huge compute needs. This is where quantum computing starts to look potentially transformative.
Precisely. It offers a fundamentally different way to compute.
So let's dive into that. How is quantum computing fundamentally different? What's the magic sauce?
Yeah.
It starts with the qubit.
It all starts with a qubit. A classical bit, as you know, is firmly a 0 or a 1, a qubit.
Yeah.
Well, thanks to superposition, it can be a 0, a 1, or crucially, a combination of both at the same time. Its state is described by probability amplitudes for being 0 and 1.
So it's not just on or off. It's like a dimmer switch. It can be anywhere in between.
That's a decent way to picture the concept, yeah, though the underlying math is richer. But the really mind-blowing part is scalability. If you have n classical bits, you have n pieces of information. If you have n qubits, that system can represent a superposition of all 2 to the power of n classical states simultaneously.
Whoa, that's exponential growth. 2 states at once.
Exponential. That's the source of the potential power. Of course, the catch is, when you actually measure the qubit system, the superposition collapses, and you only get one specific outcome, a string of 0s and 1s, based on the probabilities defined by those amplitudes.
So the power is kind of hidden until you look. And this ability to hold multiple states at once, that's what leads to quantum parallelism, performing calculations on all those possibilities simultaneously.
Exactly. You apply quantum operations to the superposition, and it's like you're doing the calculation on all 2 inputs at the same time.
Okay. Then there's entanglement. That always sounds like science fiction.
It feels like it sometimes. Entanglement is this incredibly strange connection between qubits. Once entangled, their fates are linked. If you measure the state of one, you instantly know something about the state of the other, no matter how far apart they are.
Like those magic coins that always land opposite, even across the galaxy.
It's weirder and more profound than just simple correlation. But yeah, that captures the sense of non-local connection that seems impossible classically. Entanglement is a vital resource. It lets quantum systems capture extremely complex correlations within data relationships that would be basically impossible for a classical computer to track efficiently.
Superposition for possibility, entanglement for complex links. What about interference?
Interference is how quantum algorithms actually harness that parallelism to get an answer. Think of the different computational paths within the superposition having probability waves or amplitudes. These waves can interfere, just like water waves. They can add up constructively, making the probability of getting the right answer bigger, or cancel out destructively, reducing the probability of wrong answers. Designing a quantum algorithm is all about choreographing this interference.
Wow. So you set up the superposition, use entanglement to link things up in complex ways, and then use interference to steer the whole thing towards the answer you want when you finally measure it.
That's the essence of it, yeah.
And controlling all this, manipulating the qubits, is done using quantum gates in a quantum circuit.
Exactly. They're the quantum equivalent of classical logic gates, like any or not, but they perform unitary operations, which are always reversible. You have single qubit gates, like the Hadamard gate, which is great for creating superposition, and multi-qubit gates, like the CNOT gate, which are essential for creating entanglement. A sequence of these gates applied to qubits forms a quantum circuit, the quantum program.
Got it. But building these things,
Yeah.
the actual hardware, superconducting circuits, trapped ions, it's hard, right? We're in the NISQ era.
Exactly, NISQ. Noisy intermediate scale quantum. Intermediate scale tells you we don't have that many qubits yet. Maybe tens, hundreds, perhaps pushing towards 1,000 soon, but definitely not the millions you'd need for full fault tolerance.
Noisy.
ED is the big one. These qubits are incredibly delicate. They're sensitive to vibrations, temperature changes, stray fields. Anything can disturb their quantum state. This means they have limited coherence times, they lose their quantumness pretty quickly.
So you only have a short window to do your calculation.
Right. And the quantum gates themselves aren't perfect. They introduce small errors every time they operate. This noise accumulates. Plus, the physical layout often means qubits aren't all connected to each other, so you need extra gate operations just to shuffle information around, which adds more time and more noise.
So this NISQ reality, few qubits, lots of noise, short calculation times, heavily restricts what you can actually do with a quantum computer today.
It absolutely does. It's the fundamental challenge we're grappling with.
Okay, so given those pretty severe limitations, how do you even start applying this potentially revolutionary but currently noisy tech to something like AI? That's where quantum machine learning, QML, comes in, the bridge.
QML is exactly that bridge. It's the whole field dedicated to exploring how we can use quantum computing, the principles, the algorithms, the hardware, to tackle machine learning problems.
And the aim isn't just doing ML on a quantum computer because we can, right? It's about finding a real quantum advantage.
That's the core goal. Finding situations where quantum approaches could offer genuine benefits over the best classical methods. And it's not just about speed.
What else?
Well, yes, QML looks for potential speedups, maybe in things like solving linear equations, which pop up a lot in ML. But maybe even more importantly, it explores enhanced model capacity or expressivity.
Meaning the quantum model can represent more complex patterns.
Potentially, yes. Because quantum states exist in these exponentially large spaces, maybe a quantum model with, say, 50 qubits could represent functions or data patterns that would require a classical neural network with millions or billions of parameters. So it's about potentially learning deeper, more intricate structures in the data.
That sounds powerful. What else?
Also, potentially better ways to map data into feature spaces where patterns are easier to separate, maybe more efficient ways to optimize models or sample from distributions. Some research even hints that quantum models might achieve similar results to big classical ones, but with fewer trainable parameters, which could be a win for efficiency.
Okay, so it's a broader set of potential advantages than just raw speed. Deeper models, maybe more efficient models.
Exactly. But, and this is a big but the sources emphasize, especially for QGAI, the data loading bottleneck. How do you actually get huge amounts of classical data into a quantum state efficiently without needing a ridiculously long time or destroying the quantum properties you need? That's a fundamental hurdle.
Right. If it takes longer to load the data than to run the classical algorithm, you haven't gained anything.
Precisely. It's a key challenge for applying quantum techniques to classical data sets.
All right, so we've got the pieces. Classical generative AI making new stuff. Quantum computing with its weird superposition and entanglement power, but also its noise problems, and QML trying to bridge the two. Now let's zoom in. What is quantum generative AI specifically?
Okay, QGAI is really a subfield within quantum AI. Its specific focus is using quantum algorithms, or often hybrid quantum classical ones, to learn data distributions and then generate new synthetic data matching those distributions. It's about harnessing superposition, entanglement, interference, specifically for generative creative tasks.
Got it. So it's quantum methods applied directly to the problem of creation. How do those quantum properties actually help in the generation process itself?
Well, superposition is key for representing the possibilities. A quantum state can, in principle, encode the entire probability distribution of the data you want to generate within its complex amplitudes. Think of it like holding a vast landscape of potential data points all at once.
Okay, holding the potential. An entanglement. You said it captures complex correlations.
Yeah.
How does that help make, say, a realistic image?
That's crucial. Real-world data, like images or even text, has incredibly complex relationships between its parts. Pixels aren't independent. Words depend on context. Entanglement provides a natural quantum way to represent and learn these really high-dimensional, intricate correlations, something that can be very hard for classical models to capture efficiently, especially as the complexity grows. It boosts the learning power of the quantum neural networks often used in QGAI.
Makes sense. And quantum parallelism might speed things up.
That's the hope. It could potentially accelerate parts of the training process or maybe the sampling process by exploring many possibilities concurrently. And then, the final step is quantum measurement.
That's how you get the actual data sample out.
Exactly. You've prepared this quantum state that encodes your desired distribution. When you measure the qubits, the system collapses into one specific classical outcome, say a particular image or text string. And the probability of getting that specific outcome is governed by Born's rule. It's proportional to the squared amplitude of that state in your quantum superposition.
So the quantum state holds the probability map via superposition. Entanglement weaves in the complex internal structure. Parallelism might speed up working with it. And measurement plucks out a final sample according to those quantum probabilities.
That captures the flow nicely, yes.
Okay, it's starting to click. Now, why should we be excited about this? What are the big theorized advantages QGAI might have over the classical models we talked about, based on the sources?
Probably the most fundamental hope is for enhanced expressivity. The idea is that quantum circuits, because they operate in that exponentially large Hilbert space, might be able to represent significantly more complex, high-dimensional probability distributions than classical networks of a similar, size or complexity.
Meaning they could potentially generate higher quality samples, more detailed, more diverse, capturing finer details.
That's the potential, yes. Higher fidelity generation.
And faster training or sampling, you mentioned that.
That's another key theorized advantage. Quantum parallelism, combined with quantum optimization algorithms, might speed up the training process. Some theoretical work on specific QGN models even suggested exponential speedups, though that's often under ideal conditions.
Right. Theory versus noisy reality.
Exactly. But experimentally, some results, like with a model called QCGAN, have shown promise, sometimes needing fewer parameters or training iterations than classical counterparts for certain tasks. And importantly, for some types of distributions, sampling from the trained quantum model itself could be faster or more efficient than classical sampling techniques. That's a big focus for approaches like using IQP circuits.
What about generating really complex data, like scientific simulation data or maybe even financial models?
Quantum approaches might be inherently better suited for that, capturing highly complex, high-dimensional distributions or distributions that are naturally quantum mechanical in the first place, something classical models would really struggle with. And QGAI has a unique capability. It can generate quantum data, directly actual quantum states. That's crucial for advancing quantum simulation, quantum communication, quantum computing research itself.
Okay, that's a capability classical AI just doesn't have.
Right. Plus, there's some evidence suggesting QDAI models might sometimes need fewer parameters to achieve similar performance, and they hold out hope for perhaps overcoming some stubborn classical limits like Jan mode collapse or the blurriness sometimes seen in VAEs.
Okay, the potential sounds amazing. Enhanced quality, maybe speedups, handling complexity, generating quantum data. But how do we know if it's real? What does quantum advantage actually mean for generative models? It sounds like a high bar.
It is a high bar. Quantum advantage here isn't just a theoretical possibility. It means a concrete, practical demonstration where a QGAI model measurably outperforms the very best classical generative models on a specific, meaningful task. And the outperformance needs to be significant enough to justify using the much more difficult and resource-intensive quantum hardware.
Outperforms. How? Faster. better pictures?
It could be several things. A substantial speedup in training time, or maybe more likely first, in sampling time, ideally a speedup that grows dramatically with problem size, like superpolynomial, or demonstrably better sample quality measured using standard metrics like FID for images or other relevant metrics for different data types.
Or doing something classical models just can't.
Yes, higher expressivity learning probability distributions that are provably hard for classical models to capture. Or better scaling, the quantum model handles increasing complexity more gracefully than classical ones. Or maybe solving generative problems that classical methods simply fail on, or even achieving similar results but using drastically fewer resources, fewer parameters, less training data, maybe less energy.
Well, there's that barren plateau problem you mentioned. That sounds like a huge roadblock to actually training these potentially more expressive models.
It's a major, major hurdle for many QGAI approaches, especially those using variational quantum circuits like QCBMs or many QGANs. The issue is that as you make the quantum circuit deeper or add more qubits, which you need for more expressivity, the landscape of the training objective function becomes incredibly flat. The gradients, which tell you how to adjust the parameters to improve, just vanish exponentially.
So trying to train it is like trying to roll a ball downhill on a perfectly flat plane. It just doesn't know which way to go.
Exactly. It makes gradient-based optimization incredibly difficult, if not impossible, beyond very small circuit sizes. Finding ways to avoid or mitigate these barren plateaus is one of the most critical research areas for making QGAI practical.
So demonstrating real practical advantage on today's noisy, smallish quantum computers, especially with the barren plateau threat looming, it's incredibly challenging. There's a big gap between the theoretical promise and what's feasible right now.
Absolutely. The NISQ reality and these training challenges like barren plateaus form the constant background noise, literally and figuratively, for all QGAI research today.
Okay, bearing those challenges in mind, let's look at the different ways researchers are actually trying to build QGAI models. What are the main approaches the sources cover?
Well, first up, you have Quantum GANs, or QGANs. These are probably the most direct translation of a classical idea. You take the GAN framework generator versus discriminator, and you implement parts of it using quantum circuits.
So the generator could be a quantum circuit trying to fool a classical discriminator. Or maybe both are quantum.
Both are possibilities. You could have a quantum generator, a quantum discriminator, or a mix. The goal is to leverage quantum properties like superposition and entanglement within that adversarial game, hoping for advantages like better sample quality or more efficient training. They can be fully quantum, maybe for generating quantum states, or hybrid quantum classical, which is more realistic for classical data generation on current machines.
But they probably inherit the tricky training issues of classical GANs, plus the quantum challenges.
Pretty much. You get the potential instabilities of adversarial training, plus the difficulties of training quantum circuits like barren plateaus and sensitivity to NISQ noise.
Okay, what about quantum circuit-borne machines, QCBMs? That sounds different.
It's a more direct quantum approach. Here, the generative model is the quantum circuit itself, specifically. A parameterized quantum circuit, or PQC. You set the parameters in the circuit, run it to prepare a quantum state, and then you just measure the qubits.
And the results of the measurement directly give you samples from the distribution the circuit represents.
Exactly. According to Born's rule, the probability of getting a particular measurement outcome, like a specific string of zeros and ones, which you can map to data, is determined by the quantum state prepared by the PQC. So the PQC implicitly defines the probability distribution.
How do you train it then?
You adjust the parameters of the PQC, the angles of the quantum gates, usually so that the distribution of measurement outcomes gets closer and closer to the distribution of your target data. You typically use a loss function that measures the difference between distributions, like the maximum mean discrepancy, MMD.
So the circuit is the generator and measurement is the sampling. Seems elegant, but...
But they are very susceptible to barren plateaus during training, especially as they get larger, and highly sensitive to noise. Theoretically very expressive, but practically hard to train on NISQ devices.
Got it. Then quantum Boltzmann machines, QBMs. These sound like they connect to classical energy-based models.
They do. They're quantum analogs of classical Boltzmann machines. They define probability distributions based on the physics of quantum systems specifically, using quantum Hamiltonians, which describe the energy of the system, and their corresponding thermal equilibrium states. The idea is to tune the Hamiltonian so its thermal state represents your target data distribution, and then sample from that state.
And you mentioned these might have an advantage regarding barren plateaus.
Yes, that's an intriguing finding from some recent research. It suggests that QBMs, particularly certain types or training methods, might potentially avoid the exponential gradient decay of barren plateaus that plagues many PQC-based models. If true, that would be a huge plus for trainability.
A potential path around a major roadblock.
Yeah.
But sampling from these quantum thermal states, that sounds hard too.
It presents its own set of challenges, yes. It often requires different types of quantum hardware, like quantum annealers, or different techniques on gate-based computers compared to just running and measuring a PQC.
Okay, interesting trade-offs. What about quantum diffusion models? Since diffusion is so hot classically.
This is definitely a newer, very active area. Researchers are exploring ways to bring quantum mechanics into the diffusion process, maybe using quantum operations or quantum noise channels in the forward noising or reverse denoising steps, perhaps using a PQC as the denoising model.
And this is where that using the hardware noise idea comes in.
Exactly. That's the really cutting-edge, almost provocative idea explored in papers like the RX5.2505.221931. Instead of seeing the noise in current quantum hardware as just a problem to be mitigated, what if you could leverage it? What if the natural, noisy quantum evolution on the chip could actually be a part of the generative diffusion process itself?
Wait, really? Using the unavoidable errors as a feature, how could that possibly work?
It's counterintuitive, I know. But the thinking is that the complex, noisy dynamics of the quantum system might actually help in exploring the data space, or act like a useful form of regularization during diffusion. The research suggests this approach can lead to more robust models on real hardware and potentially even better sample quality compared to trying to simulate perfect quantum dynamics or just using classical methods.
Wow. Okay, turning a bug into a feature. That's clever. Pragmatic.
Very pragmatic. It's a direct response to the NISQ reality.
Are there other approaches mentioned in the sources too?
Yes, a few others. There are methods based on variational quantum eigensolvers like GQE, the generative quantum eigensolver. These are a bit different. They often use a classical generative model, maybe a transformer, not to generate the final data, but to generate or optimize the quantum circuit itself.
So an AI designing the quantum program.
Kind of, yeah. It's metageneration. The goal is often related to optimization problems, like finding the lowest energy state of a molecule. But the circuit it designs could then potentially be used generatively, maybe like a QCBM. It's partly aimed at automating the complex task of designing good quantum circuits and possibly sidestepping issues like barren plateaus by keeping the main optimization classical.
Very meta indeed. What else?
There's the use of quantum kernels in generative models. Quantum circuits can map classical data into a high-dimensional quantum feature space. A quantum kernel then measures the similarity between data points in this quantum space.
How is that used for generation?
It's most often used inside the discriminator of a QGM. The idea is that the quantum kernel might help the discriminator better distinguish between real and fake data encoded into quantum states, making the GAN training more stable or effective. Challenges here include a potential loss of sensitivity called exponential concentration, and yes, barren plateaus if the kernel itself has trainable parameters. And finally, some work on quantum Hamiltonian-based models, QHBMs. These are hybrid models using parameterized Hamiltonians and quantum neural networks to learn correlations. They can offer a more physically grounded framework, especially for quantum data, and might sometimes require shallower circuits than QGNs for similar tasks.
Wow. Okay, that's quite a menu. QGANs adapting the classic game. QCBMs using the circuit directly as a sampler. QBMs using quantum physics, potentially avoiding plateaus. QDMs maybe even using the noise. And these meta approaches or kernel methods.
It really shows the field is trying many angles, isn't it? From direct quantum simulation to clever hybrid strategies, all aiming to leverage quantum mechanics for generation, but all bumping up against the realities of current hardware.
Right, let's talk more about that NISQ impact. How do those limits, few qubits, noise, short coherence, really handcuff these big ideas in practice?
Fundamentally, the limited qubit count just means you can only run small versions of these models. You can't tackle truly large-scale problems yet. The noise and short coherence times mean your quantum circuits have to be shallow. You can only perform a limited number of gate operations before the errors pile up and drown out any meaningful quantum computation.
So any quantum algorithm that needs a really deep, complex circuit to show its advantage it's just not feasible right now.
Not practically, no. And the limited connectivity between qubits on the chip often forces you to add extra swap gates just to move quantum information around so the right qubits can interact. Each swap adds time, adds noise. It all conspires to limit the complexity and depth of circuits you can reliably run.
So this forces the focus onto hybrid approaches, where the quantum computer only does a small part.
Exactly. Most QGA research today is heavily focused on hybrid quantum classical algorithms. The idea is to isolate a specific part of the generative task where quantum might offer an advantage, run just that small part on the quantum processor, and do the bulk of the computation classically. It requires shallow circuits, and scaling these hybrid models up remains a massive challenge.
So given this noisy reality, how are researchers trying to cope to get some useful signal out of these machines?
A huge area is quantum error mitigation, or QEM. These aren't full error correction that requires far too many qubits for NISQ machines. Instead, QEM techniques try to reduce the impact of the noise on the final result.
How do they do that?
There are various methods. Things like zero noise extrapolation, where you run the circuit at different noise levels and try to extrapolate back to the zero noise result.
Wow.
Or readout error mitigation, which corrects for errors that happen just when you measure the qubits. Or techniques to actively suppress noise during the computation. They're essential tools for getting anything meaningful from NISQ hardware.
So trying to clean up the unavoidable mess after the fact or during the run.
Pretty much. And using highly accurate classical simulators that include realistic noise models is also crucial for developing and testing algorithms before you even touch the real hardware. Plus, there's ongoing work in designing algorithms themselves to be inherently more robust to noise, or designing circuits to be as efficient as possible on specific hardware layouts.
And then there's that wild idea we keep coming back to, leveraging the noise with quantum diffusion models. Is that really seen as a serious path forward?
It absolutely is. It's maybe one of the most interesting, pragmatic responses to the NISQ situation. Instead of just fighting noise, can you incorporate it? Can the natural, messy quantum evolution on the chip actually be beneficial? That research using real IBM hardware for image generation suggests maybe so.
So the noise itself becomes part of the generative process.
Potentially, yes. For certain algorithms like diffusion, the physical quantum dynamics, noise and all might actually be a feature, not just a bug. It could lead to models that are naturally adapted to the hardware they run on. It's a very clever way to think about making progress with the imperfect tools we currently have.
Okay, that's a fascinating perspective. Let's sort of pull back and look at the overall state of the field. We know QGAI builds on classical AI milestones from the 2010s, GANs, VAEs, diffusion, and decades of quantum theory. QML got going in the 2010s, and these specific QGAI models started appearing seriously in the late 2010s.
And that barren plateaus discovery around 2018 was a really critical moment, highlighting a fundamental training challenge that the field had to confront head on.
So where's the cutting edge right now, say in this 2023-2025 window we're in? What are the big pushes?
Well, the field is definitely maturing beyond just pure theory. We're seeing more small-scale experiments on actual NISQ hardware. A huge focus is on developing QGAI algorithms that are, firstly, scalable enough to have a shot at showing advantage on larger problems eventually, and secondly, noise-resilient enough to actually work on the noisy machines we have now or expect in the near future.
Like that train classically, deploy quantumly idea.
Exactly that kind of thinking. That approach, using IQP circuits, instantaneous quantum polynomial time circuits, discussed in RDFB.2503.02934. It's clever because these circuits have properties allowing them to be trained efficiently using classical methods, potentially avoiding barren plateaus during training. But the sampling from the train circuit might still offer a quantum advantage, and they're exploring if this could scale up towards, say, 1,000 qubits.
So shifting the hardness from quantum training to classical training, but hoping for a quantum win at generation time.
That's the strategy. And the quantum diffusion model work leveraging hardware noise, like in ARS5.2505.22193, showing experimentally on real hardware that including the quantum dynamics and noise actually improved results, lower FID score, on a standard benchmark like MNEST compared to classical dynamics. That's a really concrete validation of the noiseless feature idea.
And just improving the existing models like QGANs.
Yes, refining architectures. The QCGAN work mentioned in ARC6.2402.01791 reported better performance metrics on generating handwritten digits using fewer resources compared to classical GANs in their specific setup. So it's about finding these specific niches, the right algorithm, the right problem, maybe a clever hybrid approach language combined with error mitigation or maybe even noise leveraging, where current NISQ devices might just start to show a tangible, even if limited, benefit.
Wow. Okay, we've covered a lot of ground. We started with the classical Gen AI making cool stuff, then dove into the weird world of quantum mechanics, superposition, entanglement, all that. We saw how QGAI tries to blend them, exploring this whole zoo of models, QGANs, QCBMs, QBMs, those new QDMs, even the meta-generation stuff.
Right, and we constantly hit the reality check. The challenges of NISQ hardware, the noise problem, the barren plateaus.
And even that fascinating twist of maybe using the noise itself.
Yeah, the whole quest for QGAI, it's really driven by this deep potential, isn't it? The hope for exponential speedups, the possibility of modeling complexity that's just out of reach for classical computers today.
And generating totally new kinds of data or insights, maybe even things tied to the quantum nature of reality itself.
Exactly.
So why should you, listening right now, care about this super cutting-edge, kind of abstract-sounding field?
Well, because breakthroughs here, they're not just going to stay in the lab at science experiments.
Right.
They could genuinely revolutionize huge areas. Think about drug discovery or material science. Being able to accurately simulate and design molecules at the quantum level could change everything.
Or complex data analysis, finance, climate change modeling.
Potentially, yes. And maybe even unlocking forms of digital creativity, new kinds of art or music generated by models with fundamentally different capabilities. We don't even know what that might look like yet. It's really about pushing the absolute boundaries of what we can compute and maybe even what we can create.
Which does leave us with a pretty mind-bending final thought to chew on.
Go for it.
If quantum mechanics really does describe the fundamental fabric of reality, what kinds of generative creativity, what kinds of patterns or structures might only truly emerge when our AI can finally tap directly into that quantum foundation? What's hiding in the universe that only a quantum generator could possibly find or even bring into existence?